Welcome to this lecture number 12 on this NPTEL course in fluid mechanics for chemical engineering undergraduate students. In the previous lecture, that is lecture number 11, we were discussing an important topic called the Reynolds transport theorem. So, just to give you a background on what we were discussing. Okay. So, essentially there are two ways of analyzing problems in mechanics. One is called the system or control mass approach or system approach. Okay. Here we are following a same set of particles, material particles, fluid particles, okay, and as time proceeds, this particular volume, that's which we call the system, which has the same set of material particles or fluid particles, as the fluid flows after a time t, the same volume will be stretched and deformed, okay, in shape, and it will change its orientation and so on. It will move as the fluid flows, but essentially you are following the same set of fluid particles, okay, as the fluid is moving. Okay. This is not very unlike what one does in simple particle mechanics, Newtonian mechanics, where you identify a mass like a sphere, and then we worry about the forces that are acting on those sphere, and then we can compute the trajectory or motion of the particle by applying Newton's laws of motion. Okay. So, likewise one can imagine doing that for a fluid, although a fluid is not a discrete entity in the continuum hypothesis. It is a continuous medium. So, a chunk of fluid can be identified, and which has the same set of mass points or material points, and as time proceeds due to motion, this control mass, or sometimes this is also called as material volume, will evolve in time, and we can, once you identify the forces, the body forces and surface forces that are acting on the same set of mass points, you can compute the motion of this by applying Newton's second law. Okay. But the difficulty in fluid mechanics is that we do not want to follow the same set of mass points, because most applications in fluid mechanics, okay, for example, you may have a pump, okay, which is delivering the fluid. So, you may want to understand what is the power requirement in a pump, okay, or you may have a pipe, okay, and you may want to worry about what are the drag forces that are exerted by the flow on a particular section in a pipe. In such instances, you are not worried about the same set of, for example, if you identify this green patch will move through the pump and it will eventually go away, and so will a patch in a fluid in a pipe. This will not continue to remain in the pipe, it will go away. So, whereas we are interested in fixed regions in space in most engineering applications. So, it becomes important for us to identify what are called control volumes, which is a fixed region in space, okay, which can comprise of a device like a pump or pipe and so on. Okay. So, for example, you may have a piping network like this, okay, and you can identify a fictitious boundary where fluid is entering and leaving. There is, it is not a physical boundary, but it is merely that surface that demarcates the region of interest from outside. It is called the control surface, and once you have this, there are these physical boundaries comprised by the wall of the tube, okay, and you can identify this as your region of interest, but fluid continues to come in and leave. So, if you consider a patch of fluid, it will come and then it will leave, okay. It may not stay in the same region of space, physical region of space, it will continue to move. But whereas this is very convenient, because we are interested in understanding properties such as what must be the work that we must perform on the fluid in order to make it flow at a given flow rate. So, in a pump, for example. So, in such cases we want to identify a fixed region in space, and we want to analyze flow problems. Okay. So, that is called the control volume approach. So, here we are not following the same set of mass points as in the control volume or systems approach. This is the control volume approach. This is the preferred approach in fluid mechanics. Okay. Once we choose this approach, then again we land up with the same issue. For example, when we did Eulerian versus Lagrangian description, we realized that even if you want to work only with like Eulerian description, we cannot compute accelerations by just taking partial derivatives, because accelerations correspond to identifiable piece of a point and a point with a fixed identity and the rate of change of its velocity, not merely the rate of change of velocity with time when expressed in Eulerian coordinates. So, we had a tool called the substantial derivative, which enabled us to calculate the rate at which particles changes its acceleration as you follow the particle at a given point in time and space. Okay. So, likewise here we want to extend a similar idea to not just a single point, but a macroscopic volume. Okay. So, the reason is that eventually we want to write down fundamental principles of mechanics, such as the law of conservation of mass, law of conservation of momentum, which is Newton's second law of motion, and law of conservation of energy, which is first law of thermodynamics. Okay. So, in such instances, all these laws are applicable to identifiable piece of matter in their most natural form. So, for example, Newton's law says that mass times acceleration is equal to sum of forces on an identifiable piece of matter, not on a fixed region in space. So, we need again a tool or a vehicle that transforms control volume information to control mass information, okay, so that we can naturally apply quantity principles such as Newton's second law. Okay. So, this is done by using what is called the Reynolds transport theorem. Okay. This was what we proceeded with in the last lecture. Let me quickly recapitulate what we did. Okay. The Reynolds transport theorem is a way of relating time derivatives of quantities such as mass in a given region of space, okay, to that with associated with the system or the material that is present in the system. For example, we said that you identify a fixed region of space. Okay. This is our CV indicated in blue, and let us identify our system or the control mass to be that coincides with the CV at a given instant of time. Okay. This is time t0. At time t0, the system and CV is short for control volume, coincide. Okay. At a later time, you still have the CV is a fixed region in space, but the system would have moved depending on the way the fluid flows. I am just showing schematically here, something like this. Okay. So, this is at time t0, this is at time t0 plus delta t. The CV is denoted in blue, it remains the same. The system, that is because of fluid flow, if you follow a set of points, they will in general move away from the system from the CV. Okay. So, we want to be able to write rate of change of instantaneous rate of change of mass, momentum or energy of the fluid that is present in the CV, okay, of the fluid that is present in the system in terms of the variables of the CV, because we want to follow only the control volume approach, while the fundamental principles are most naturally applicable to the control mass approach. So, we want to be able to write the derive a relation, that is the purpose of Reynolds transport theorem. To this end, so we want to apply conservation of mass, momentum and energy to the system that is present in the CV at time t0, although the system is moving away from the CV at a later time. So, mass is simply the mass of fluid is m, momentum is m times v, so small it is lowercase m, and energy is half m v dot v. Okay. Now, we define a generic quantity eta for which we will derive the Reynolds transport theorem. This could be any quantity per unit mass. For example, for mass eta is 1. Okay. For momentum, this is mass per unit mass. Okay. For momentum, eta is mv divided by m, eta is v. For energy, kinetic energy, okay, this is kinetic energy of motion in the fluid. For kinetic energy, okay, eta becomes half v squared, v dot v I will denote as v squared. Okay. So, once we have this, then we are interested in the total amount of quantity that is present in the system of mass, momentum or energy, that is obtained by taking a volume integral over the system. So, in my notation, V with a cross is the volume, because the V without a cross will be denoted for velocity, will be reserved for velocity. So, to distinguish volume from velocity, I will use a cross. So, this is the volume over the system, eta, which is quantity per unit mass, times rho, which is mass per unit volume, integrated over the volume. This will give you the total amount of either mass, momentum or energy, depending on what you put for eta. Okay. So, this is a volume integral, and we are interested in dN by dt of the system, and how this is related to CV variables. That is the net outcome of the Reynolds transport theorem. Okay. So, what we do is first go back to the figure. So, let us just keep a reference on this figure. So, imagine that at a time t0, okay, the system and CV are coinciding, but at a later time the system has left the CV, but there is some, since we are only looking at an infinitesimal time difference, there will be some region 2 where the system and CV still are coinciding. There will be a region 1 where the system has left the CV, and there will be a region 3 which the system has created afresh because of its motion. So, there will be 3 volumes one can identify in this composite thing, and we will try to simplify based on. Okay. So, we will simply look at this diagram, and we will try to simplify our time derivative of all quantities in terms of this particular picture that we have. So, by fundamental definition, the rate of change of the total quantity of either mass, momentum or energy present in the system is limit delta t going to 0. The instantaneous rate of change is the total amount present in the system at t0 plus delta t minus total amount present in the system at t0 divided by delta t. So, that is the fundamental definition. Now, from the figure that I just drew, at t0, okay, the system coincides with CV, because the system and CV coincide at time t0. System and CV coincide at time t0, but at a later time. So, the amount of quantity present in the system and CV are identical because of this reason. Okay. But at a later time t0 plus delta t, okay, the system is comprised of N2, which is the common region between the system and CV at time t0 plus delta t, plus N3 at time t0 plus delta t. But N2 is nothing but NCV minus N1. So, recall in our picture here that N2 is basically, okay, N2 is that region which is the total CV volume minus the volume that is vacated by the system at a later time. So, N2 is NCV, which is this entire thing, minus N1, okay, and N3 is the new space that is created by the system due to its motion from the CV. Okay. So, N2 can be written as NCV minus N1 plus N3 will remain as such at T0 plus delta T. Okay. So, I am going to substitute all this in the fundamental definition of time derivative. So, rate of change of the total amount of something that is present in the system is limit delta T going to 0 NCV minus N1 plus N3 at T0 plus delta T minus NCV at T0 divided by delta T. So, this can be split into 2 or 3 terms. So, limit delta T going to 0 NCV at T0 plus delta T minus the amount of various quantities present in the CV at T0 divided by delta T. This is one term. The second term is plus limit delta T going to 0 N3 T0 plus delta T by delta T minus limit delta T going to 0 N1 T0 plus delta T divided by delta T. Okay. So, if you look at this expression here, you are just looking at the rate of change of the quantity present in the CV at two different times divided by delta T. So, from fundamental definition of calculus, this is d and CV divided by dt. Okay. So, that is essentially the rate of change of the quantity that is present in the CV. That is very simple. So, to be precise, we can put partial derivative. Okay. So, now we have to simplify these two terms. Let us call this term, okay, let us just look at this term. Okay. So, if you recall, the system was here, sorry, the CV was here, the system has moved, okay, and this was region 3. Region 3 is the newly created region. So, what is this? This is the amount of change that is of in any quantity like mass, moment or energy, because of the fact that the system has moved to this new region in space. Okay. So, how do we calculate this? So, why is the system or control mass moving? The control mass is moving because if you take a patch of surface on the CV, okay, let us say you take a patch of surface on the CV. Now, that patch is moving to a newer region, okay, because of the fact that the fluid on the surface of the CV has some normal velocities, has a component of velocity in the normal direction. Okay. If you consider the CV to be like this, if the fluid is purely tangentially moving on the surface, there cannot be any motion in this direction. Okay. But if there is a normal motion, if at a point the velocity is like this, then there will be a component that is moving in this direction. That means that the system will change its location at a later time by that amount. Okay. So, you take, this is the surface of the CV, this is at at all times, the CV is remaining fixed in space, that is called the CS, surface of the CV is called control surface, okay, and this is the region 3. Okay. And why is this moving? This is moving because this is the unit area. So, this is the area patch. Area is denoted by a magnitude and a direction, because whenever you have area, okay, you can denote its direction by telling the way in which the normal is pointing. You can say the normal is pointing from in to out or out to in. We will normally take in to out, that is called outward unit normal. Okay. So, this area is a vector, area element is a vector, and the velocity in general can point in some direction. Okay. So, this volume that is created over a time delta T, okay, must be because of the fact that the fluid element on this surface has a component in the normal direction. Okay. So, V dot dA is essentially times delta T will be the volume, okay, will be the volume that is traversed by a tiny patch of area on the control surface of the CV, okay, as the system proceeds to leave the CV and occupy a new nearby location. Okay. So, this length is mod V times delta T, okay, if the magnitude of the vector V times delta T. Okay. So, to calculate the volume, okay, so d, the amount of material, so amount of the extent of change in any quantity like mass, moment or energy in a tiny volume due to the motion of the system, okay, from the CV is given by the volume, okay, is given by essentially the amount of quantity per unit mass times mass per unit volume times the volume at T0 plus delta T. Okay. But we know what the volume is, it is eta times rho, okay. dV is something that we just calculated as V dot dA times delta T. Okay. This is dN3 T0 plus delta T. This is the extent of change that you will encounter because of the motion of the fluid through a tiny patch of the control surface, and therefore, there is a new tiny volume that is created, and what is the change in mass momentum of energy due to this volume, that is this term. So, you multiply, you take the quantity either mass momentum or energy multiplied by the per unit mass, okay, that is eta, multiplied by rho, that gives you per unit volume, times the volume itself, which is this. Okay. Now, the total amount is, so we are interested in, if you remember, the quantity limit delta t going to 0 n 3 of T 0 plus delta t divided by delta t, that is the quantity that appeared as one of the terms. Okay, if you remember the previous slide, so you had this term. So, we are now trying to simplify this term. Okay. So, what is that term? That term is nothing but we have eta, okay, and so this is d n. In order to get n, you will do an integral over the control surface, the entire control surface 3, because now if you recall, so the CV and the system, this is the region 3 which is being created, this is the region 1 which is being deleted by the system due to its motion. So, we will do the integral over the entire control surface 3 of d and 3, okay, at T 0 plus delta t divided by delta t. This will be our result, and in order to simplify this further, we will substitute d n from here to here. Okay. So, this term which we are after is simply integral C s 3, okay, eta rho v dot dA delta t divided by delta t. The delta t will cancel out to give limit delta t going to 0 and 3 divided by delta t is nothing but integral over the control surface 3 eta rho v dot dA. Okay. Now, what this means physically is that, so v dot dA is the volumetric flow rate. Suppose you consider a tiny patch on the control surface 3, okay, dA, and n is dA is the unit area. So, dA is given by, vector is given by this magnitude times direction, the outward unit normal. Okay. If the velocity is like this, okay, the volume that is created per unit time, the volumetric flow rate is v dot dA, times rho will give you the mass that is flowing per unit time in this volume, times eta will give you the rate at which a quantity like mass, momentum or energy is changing per unit time by virtue of the motion of the fluid out of the CV. Okay. This is essentially the physical interpretation of this term. Okay. Now, we can do same thing for region 1. Recall that you had the system, the control volume to be fixed, the system is moving at a later time. Okay. This was region 3 which we just computed, region 2 which we already calculated, and region 1 is again the stuff that was deleted by the motion of the system or control mass from the CV. Okay. So, we can write a similar expression because the ideas are very similar. Limit delta t tending to 0 n 1 T 0 plus delta t divided by delta t is equal to. Okay. Now, the key thing here is that here the unit outward normal is in this direction, but we have assumed that the fluid is moving in this direction, the velocity is in this direction. So, v dot dA will be a negative quantity. Okay. Now, but we have already introduced a negative sign here in our earlier slide here earlier. We assume that this quantity is already, we have taken into account the negative term. So, we have to put an explicit negative sign because we have already taken that negative signs there, because we assume that fluid is the system is deleting this volume. So, since v dot dA is negative, we will put an explicit negative sign. Okay. So, v dot dA is negative rho over, okay, eta rho v dot dA. If we did not put the negative sign in the previous slide, okay, then we can simply forget about the negative sign here, because the v dot dA itself is negative, but since we explicitly took into account the negative sign there, we have to take care of an additional negative sign here. Okay, that is the idea. So, if we add all the terms that we have, therefore, okay, if we add all the terms that we have, then dn dt of the system, okay, at a given time t0, okay, is equal to d dt over the Cv of eta rho dV plus integral over Cs1. Okay, now the two negative signs will add to give a positive sign, eta rho v dot dA plus integral over Cs3 eta rho v dot dA. Okay. Now, this is Cs1 and Cs3 will form the entire control surface, because this was the system Cv, sorry, and this was the system. Okay. So, this was control surface, this part was the control surface 3 and this is control surface 1, which was deleted, this is the one that is created. So, this will form the entire control surface of the Cv. So, this is simply eta rho v dot dA. Okay. So, the rate of change of a quantity like mass, momentum or energy that is present in the system at a given time, okay, is equal to, if the system and Cv coincide at that time, is equal to, there are two terms, one contribution is the bulk rate of change of quantities in the Cv itself, eta rho dV. Then the next contribution is due to the motion of fluid in and out of the Cv due to fluid flow, okay, that is the flux term. Okay. So, just if you recall, in the substantial derivative of a quantity like temperature, if you recall, was dT dt plus v dot del T. Okay. This was the convected rate of change, this is the local rate of change. Likewise, if you take a finite volume, okay, of Cv, then you ask the question, what is the rate of change of mass, momentum or energy of the fluid material that is present in the Cv. As you follow the material, there will be two contributions. One is the local rate of change present in the Cv itself due to various reasons, and the other is because of the fact that the fluid is flowing in or net, there will be a net flux of fluid in or out depending on the problem, and this will lead to either a efflux of energy, momentum or mass, or an influx of energy, momentum or mass. So, therefore, this contributes to the convection or convected, this is similar to the convected contribution to the substantial derivative. This is because of the flow that takes fluid away, and hence therefore, it takes mass away, momentum away, as well as energy away or into the control volume. So, this is the Reynolds transport theorem. So, the Reynolds transport theorem, sometimes shortened as RTT, says that the rate of change of any quantity such as mass, momentum or energy present in the system at a time t naught is comprised of two parts, assuming that the system and Cv coincide at a time t0, okay, is equal to the inherent rate of change of such quantities within the Cv plus surface contribution, okay, eta rho v dot dA. V dot dA is the volumetric flow rate on a tiny patch about a tiny surface patch, rho times that will be the mass flow rate, and eta times eta is quantities per unit mass. So, this will be the rate at which certain quantities such as mass, momentum or energy are either carried away or carried into the control surface, control volume, depending on the problem, nature of the problem. Okay. So, the key thing that we must note here is that if you have a Cv, okay, and you take a patch of surface, so that is what I call dA here. Now, this dA is normally written as n times dA, okay, the unit outward normal from the Cv that is pointing outside. So, if v dot n times dA, so v dot vector dA is v dot n times dA. If v dot n is positive, that is v is in the same direction as n, okay, there are two cases. If v dot n is positive, is greater than 0, that means there is a net outflow, okay, there is a net outflow, okay, of fluid. If v dot n is negative, there is an inflow, okay. of fluid around that patch, and if you integrate over the entire patch, if you either find V dot n to be the entire integral to be positive, that means there is a net flow out, and if you find that it is negative, it is net flow in. And also notice that the velocity is measured with respect to the CV, that is, you put a coordinate system, okay, and the velocity is with respect to this coordinate system, okay. Velocity is with respect to the CV, okay. The reason I am mentioning this is that suppose you have a moving CV, okay, this is stationary frame of reference, okay. Suppose I have an airplane that is moving, okay. So, suppose I have an airplane that is moving, so I can construct at a constant velocity, I can construct a moving frame of reference where I put my coordinate system on the airplane itself, okay, in which case the CV itself is moving at a constant velocity, okay. Your CV is not a fixed region in space, it is following the airplane, so it is moving at a constant velocity. So, we can define relative velocity as V minus Vs. Let us say the system, the CV is moving with a velocity Vs, okay. Now, the Reynolds transport theorem for a moving frame of reference is dN system by dt is d dt over CV eta rho dV, that remains the same, plus integral over Cs eta rho Vr dot dA. Instead of having absolute velocities, you have relative velocities, because only if the relative velocity is there between the fluid and the control, and the volume and the velocity at which the CV itself is moving, will there be a net inflow or outflow. If the fluid is moving at the same speed as the CV, then there is obviously no net inflow or outflow. So, the Reynolds transport theorem changes in the sense that here for moving frame, it is the relative velocity that comes in the flux terms, otherwise it is the same, okay. So, this is a very important result in fluid mechanics, that is Reynolds transport theorem. Now, once we have this tool, we can apply it to the fundamental laws of physics that are as applicable to a fluid, okay. So, essentially we will apply law of conservation of mass, okay, to the CV, then law of conservation of momentum, which is Newton's second law, okay, Newton's second law, and conservation of energy, which is first law of thermodynamics. I will give you enough background as we go along, but essentially we will apply the Reynolds transport theorem to these fundamental principles, and then those will be the starting points for us to solve problems in fluid mechanics. Now, there are two ways to go about it. The first approach is what is called the macroscopic approach, okay. The macroscopic approach says that you apply the principles, okay, or macroscopic balances, okay, over larger regions of volume. So, those pieces of regions of volume could be so large that they can include a pump and then a pipe, and then you have whatever that you have in your problem, you can include all of this inside a huge CV, okay, and then you can apply the principles of mass conservation, momentum balance and energy balance, and you can do problem, you can try to address problems. Such balances are useful, but they are they give only gross quantities, they do not give, or they cannot give detailed information like what is the velocity at each and every point in space, what is the shear stress at a point in a wall, and so on, okay. But you can also apply the fundamental principles to instead of macroscopic volumes, you can apply to differential volumes, which will lead to what are called microscopic balances, okay. So, sometimes macroscopic balances are also called integral balances, because the equations will be in the form of integrals, while microscopic balances are sometimes called differential balances, because the equations that we get will be in the form of differential equations, okay. So, we will first apply the principles of mass conservation, momentum balance and energy balance to mass conservation first, to macroscopic CVs. So, and then we will proceed to microscopic balances. Okay. So, both these approaches have their own advantages and they have their own difficulties. So, we will try to indicate them as we go along. Okay. Now, first is conservation of mass. Okay. Now, conservation of mass, law of conservation of mass says that mass is neither created nor destroyed. When we apply this to a system, suppose you follow a system or a control volume at time t0 and at a later time, okay, this may undergo a change like this, but if you are following the same set of mass points, because that is the definition of a control mass, that is you are following the same identical set of fluid particles or material particles. So, by definition the rate of change of mass of this system or a control mass is 0, because we are following the same set of mass points, okay, as we follow the material volume, okay, or the control mass. So, the rate of change of mass of the system is 0. Okay. Now, we will use Reynolds transport theorem with eta equals 1, because n is the mass that is present in the system. So, mass divided by mass becomes unity. So, eta becomes unity. Eta is any quantity per unit mass. Okay. So, the rate of change of mass of the system per unit time from Reynolds transport theorem is, there are two contributions. One is the volumetric contribution Cv rho dV, plus the other is the surface contribution, okay, rho V dot dA. Okay. But conservation of mass says that, law of conservation of mass says that this must be 0. So, this entire quantity must be 0, because that is by principle of conservation of mass. Okay. So, we have d dt of integral rho dV Cv plus integral Cs rho V dot A to be 0. Okay. So, we can rewrite this slightly differently, take this to the other side. Okay. Now, if once we rewrite this, we can interpret this physically in a very simple way. What is the term on the left side? Integral, suppose you consider a Cv, okay, integral rho dV over the Cv is the total mass present in the Cv. Okay. So, this is the rate of change of mass, d dt of that is rate of change of mass present in the Cv, in the control volume. Now, why is the mass why should the mass change in the control volume? Well, it is because of the fact that in a real application, for example, a real Cv could be something like a tank, okay, in which there are inflows and outflows. Okay. So, there could be multiple inlets and outlets. Okay. So, this is the way real application, there could be inlets here and outlets here and so on. So, if you take this as your Cv, if you take this as your Cv, then why is the mass present in the Cv, why should it change? It should change because it should change with time, because there is a net imbalance between the inflow and outflow. So, let us look at the right side. What does it mean? Okay. I told you that V dot dA is positive, V dot dA is greater than 0, okay, if there is an outflow. Okay. If this entire surface integral is greater than 0, that means that there is a net outflow of fluid. Now, this negative sign means that if there is a net outflow of fluid from a Cv, then of course, the mass of fluid present in the Cv must decrease. Okay. That is what this means. If V dot dA is negative, okay, if the surface integral is negative, then negative of negative is positive. If V dot dA is negative, then there is a net inflow. So, if there is a net inflow through all the flows into the Cv, that means that the mass present in the Cv must increase as a function of time. So, this is a positive quantity. So, that is all it means. Okay. So, again the sign convention is such that V dot dA is greater than 0 if there is outflow across a control surface, across a CS control surface, and V dot dA is less than 0 if there is a inflow across CS. Okay. Okay. Now, let us try to simplify this in some special cases. So, special cases where that is the most general form of mass conservation equation, okay, for a CV. Now, let us simplify it for some special cases. First, let us simplify this for an incompressible fluid. Okay. For an incompressible fluid, incompressible fluid by definition means that the density of the fluid is a constant. Okay. It is not changing due to the flow. Okay. So, the most general form of mass conservation is integral rho dV dt of CV is minus integral Cs rho V dot dA. Okay. Now, since the CV is generally fixed in space, it is not a function of time, you can pull this time derivative in, okay, if you choose to, okay, but let us just keep it like that. But since rho is a constant, rho can be pulled out. So, rho d dt of integral CV dV is minus integral rho, because rho is a constant, V dot dA can be written as V dot n dA, okay, because dA, the unit area vector, so the area element is a vector, it is its magnitude times the unit outward normal. So, whenever you have a small patch of area, okay, it is denoted by a magnitude and a direction. Okay. The normal that is pointing from in to out, that is called the outward unit normal, unit vector normal, okay, to the surface. That is why it is called outward unit normal. Okay. Now, let us try to see what this term means. This is integral over CV of dV, that means this is d dt of the volume of the CV itself. Okay. But the CV is a fixed region in space, so its volume does not change with time, unlike a material volume which changes with time. So, this becomes 0. So, this left side is 0. So, the right side for an incompressible fluid simplifies to integral V dot n dA is 0. Okay. So, this is the most general form of mass conservation equation for incompressible fluids. Notice that we are not placing any restriction on whether the flow is steady or not. So, it is valid for both steady as well as unsteady. The only stipulation we make for incompressible fluids is that the density is a constant. So, the time derivative vanishes because the CV is fixed in space, not because the flow is steady. Still, the quantities inside the CV could change with so still the velocity can change with time, okay, but that does not mean that this is valid only for steady cases. Even if you have unsteady cases, if the fluid is incompressible, then V dot n must be integral V dot n dA must be 0. Now, let us try to think of reasonably concrete examples. Typically what you have is you have a CV with various inlets and outlets, okay, you have multiple inlets and outlets. Okay. So, this is let us say some sort of a container, and this is your CV. Okay. There are various inlets and outlets. Okay. Now, typically these inlets and outlets are pipes or of some cross section. Okay. So, you can have pipes or some rectangular conduits. Okay. That is how inlets and outlets will be in real applications. Okay. In general, if you want to say what is integral V dot n dA is 0, okay, you have to, this is over the entire control surface, you have to split this integral into various surfaces. So, integral over CS1 V dot n dA plus, because there are only few inlets and outlets over which fluid is flowing. So, you have to assume that we have to apply this to various inlets and outlets. Okay. At each inlet and outlet, therefore, suppose I take a given inlet, okay, suppose this is my control surface. Okay. Now, it is useful to take the velocity, okay, the control surface such that it is perpendicular to the, that is, it is the normal of the control surface is parallel to the velocity vector that is entering the CV. For example, okay, suppose you have a control surface like this, let us try to okay, suppose you have a control surface like this, okay, suppose you have CV like this, okay, suppose you have CV like this. It is useful to keep the control surface, and let us say fluid is flowing perpendicular in this manner, it is useful to keep the control surface like this. Okay. So, even if you have a CV in which suppose you have a jet that is flowing like this, okay, suppose you have a jet, okay, that is impinging on a surface and, okay, and it is flowing like this. Suppose you have a conical surface, okay, and a jet is impinging and it is leaving. Okay. Suppose you want to keep, you draw a CV with a CS, it is useful to keep the CS to be perpendicular to the outflow of or inflow of the fluid, because so this could be your CV, okay, where the control surfaces are drawn such that they are perpendicular to the outflow, because only then this V dot n becomes a easier quantity to evaluate. Okay. So, that is one simplification that one can achieve. The other thing is, whenever you have flow in pipes and channels, we will see later that in general V is a function of the coordinates of the cross sectional area. That is, if I have a pipe, okay, the velocity at various locations in the pipe, the pointwise velocity need not be the same, okay, they are in general different. Okay. But if the flow is uniform, if you assume the flow to be uniform, then V is independent of the cross sectional area. Okay. That means that at each and every point the velocity vector is pointing in a constant direction and the magnitude is also constant. If so, we have V dot n dA is 0. Okay. If V is a constant, okay, and if you are assuming that okay, so this can be also be written as V dot dA is 0. Okay. If you are assuming that V is a constant, it can be pulled out of the integral. This is only for uniform flow approximation. Okay. Uniform flow approximation, only in that thing where velocity is independent of the cross sectional coordinates, you can pull it out. So, integral over dA of the CS is nothing but the area of the CS. So, V dot dA is 0, but remember that the integral will have various inlets and outlets. So, we will have to count over all the inlets and outlets. Okay. So, as I just mentioned, a generic problem could have many inlets and outlets. So, the integral over CS over various, so you can split this integral into CS1, CS2 and so on. All this will therefore will become sum over various cross sectional control surfaces of V dot dA is 0. Okay. Sorry, V dot A is 0, where A is the area of that particular control surface, and of course, there is a vectorial nature to the area, because it depends on whether there is an inflow or outflow. If V dot A is positive, then this outflow, or if V dot A is negative, it is an inflow, because n is an outward normal. So, the normal to the area points from in to out. If the flow is from out to in, then therefore, the product of these two quantities will be negative. If the velocity is parallel to the area, that is outward normal, then it will be positive. Okay. So, for incompressible, for uniform flow at the control surfaces plus incompressible flow, okay, whether it is steady or not, it does not matter. So, you have integral over all control surfaces, velocity dotted with the area. Okay. The area is basically the scalar magnitude times the unit outward normal to each CS. Okay. The physical interpretation is V dot A is the volumetric flow rate. Okay. Okay. So, integral over V dot dA over any control surface is the net rate at which volume flows per unit time. out of the CV it is if it is positive, or into the CV if it is negative. So, the units are meter cube per second. Okay. So, essentially for an incompressible fluid, the mass conservation boils down to volume conservation, because density is a constant. Density is mass per unit volume. If density is a constant, and since mass conservation, so rho is mass per volume, or mass is rho times volume. If rho is a constant, then mass conservation amounts to volume conservation in incompressible fluids. That is what we are seeing. Okay. Now, sometimes it is useful to think of an average velocity integrated over the averaged over the cross section area. So, this is Q, the volumetric flow rate, divided by the area of cross section, 1 over A integral area V dot dA. V dot dA is Q. So, Q by A is 1 over A integral V dot dA. That is the average velocity at a cross section. That is the average velocity at a cross section, velocity averaged over the cross section. Okay. Now, the next simplification we will do is the steady flow. Now, the fluid may be compressible. Okay. Fluid may be compressible. Okay. So, the most general form of the mass conservation equation is integral rho dV plus integral rho V dot dA. This is over volume of CV, this is over control surface is 0, but by steady we mean d dt of a quantity is 0. So, steady means this entire quantity, the rate of change of mass is 0, because we are assuming things to be steady in the control volume. So, here you get whether it is an incompressible or compressible fluid. So, rho will occur inside the integral, rho V dot dA is 0. Okay. So, if you assume uniform properties, that is, if rho and velocity do not vary with cross sections, although they may vary across different cross sections. If at each cross section, if rho is a constant, rho V are constant at each cross section, although they may vary across different cross sections, each cross section area of the control surface, then this area integral is trivial. So, it becomes summation over all control surfaces rho. Okay. So, this becomes, rho will still happen inside, because in general rho at different control surfaces can be different. V dot A is 0. Okay. So, if you assume uniform velocity at all inlets and outlets, so in general this can be control surfaces outlets split into outlets rho V dot A. So, at outlets V dot A is positive. So, rho I V I A I, where I is the index that sums over all outlets, minus I is the index over all inlets. Since V dot A is negative, so this becomes rho I V I A I over all inlets, okay, is 0, or okay, this simply translates to summation over all inlets rho I V I A I is summation over all outlets rho I V I A I. This is for a steady flow, the mass conservation equation as applied for a steady flow. Okay, if you just have single input, single output, that is only one inlet and single outlet, we have rho in V in A in is rho out V out A out. This is for a steady flow. Okay. So, we will stop here on the mass conservation balance, mass balance for a CV. We will continue in the next lecture.